Welcome to this lecture on sampling distributions. Today, we are going to explore Fisher's t-distribution, an incredibly powerful mathematical tool that allows statisticians and scientists to make accurate predictions, even when they have very little data to work with. By the end of this video, you will understand exactly why this distribution was created, how it differs from the standard normal curve, and how to use it in real-world scenarios. Let us start by imagining a simple scenario. Imagine you are trying to guess the average weight of all apples in a massive orchard, but you only have time to pick 3 apples. Because your sample is so tiny, you cannot confidently know the true spread or variance of all the apples in the orchard. If you just use the standard bell curve to make your guess, you will be overly confident and often completely wrong. You need a mathematical tool that is more cautious and has thicker tails at the ends to account for the extra uncertainty of a small sample. This cautious, wider bell curve is exactly what the t-distribution provides. Now that we understand the need for this tool, let us look at its fascinating origins. The historical context behind this distribution actually involves beer brewing. A statistician named William Seeley Gossett worked at the Guinness Brewery in the early 1900s, analyzing small batches of barley. Because his employer forbade publishing under his real name to protect trade secrets, Gossett published his groundbreaking findings under the pen name Student. Later, the brilliant statistician Sir Ronald A. Fisher took Gossett's practical work and gave it a rigorous mathematical foundation. Fisher realized Gossett's original statistic was slightly biased, so he reformulated it using an unbiased sample standard deviation. This modified version is the exact formula we use today. To truly appreciate Fisher's work, we must first look at the baseline formula we use when we have perfect information. This formula represents the standard normal variable, denoted by Z. We use this when we know everything about the population. In this equation, x bar stands for the sample mean, which is the average of our collected data. The symbol mu represents the true population mean, or the theoretical average of the entire group. In the denominator, sigma is the true population standard deviation, and n is our sample size. When the sample size increases, the denominator shrinks, making the overall value larger. However, in real life, we almost never know the true value of sigma, which makes this formula impossible to use directly for small samples. Since we do not know the true population spread, we must adapt our approach. To solve the problem of the unknown population spread, we replace the true standard deviation with our best guess. We use the sample standard deviation, denoted by the symbol S. This brings us to the modern formula for the t-statistic, denoted by t. Here, we take the difference between our sample mean and the claimed population mean and divide it by the standard error. The standard error is the sample standard deviation divided by the square root of the sample size. Because S is just an estimate and can vary from sample to sample, the resulting value is no longer perfectly normally distributed. This is the exact formulation that Fisher rigorously defined. Let us see how this formula works in practice with a concrete example. A light bulb manufacturer claims their bulbs last 1,000 hours on average. You test a small sample of 9 bulbs and find an average lifespan of 980 hours, with a sample standard deviation of 30 hours. We need to calculate the t-statistic to see if the bulbs are genuinely defective or if our small sample was just unlucky. We start by identifying our given values and substituting them into Fisher's modern formula. We place our sample mean of 980 and subtract the claimed mean of 1000. In the denominator, we place our sample standard deviation of 30 over the square root of our sample size, 9. Continuing with our calculation, we will now simplify the expression to find our final value. We carefully evaluate the numerator and the denominator. By subtracting 1000 from 980, we get a numerator of -20, showing our sample average is lower than the claim. In the denominator, we know the square root of 9 is exactly 3. Dividing 30 by 3 gives us exactly 10, which represents the standard error of our sample mean. Finally, we divide the observed difference of -20 by the standard error of 10. This gives us a final calculated t-statistic of exactly -2.0. This means our sample average is exactly 2 full standard errors below what the manufacturer promised. Now that we have calculated a t-statistic, let us look at the deeper mathematical definition of the distribution itself. To understand this on a deeper mathematical level, we can define the t-distribution as a combination of two other distributions. The random variable t is defined as a ratio. The numerator, z, is a standard normal random variable, representing our basic data spread. The denominator involves v, which is a chi-square random variable, divided by its degrees of freedom, k. Taking the square root of this ratio perfectly models the extra uncertainty introduced by estimating the standard deviation from a small sample. If the degrees of freedom increase, the denominator stabilizes, and the entire ratio behaves more like a standard normal variable. Let us visualize exactly what this mathematical ratio looks like on a graph. As you can see in this diagram, the t-distribution curves are flatter and wider than the solid black standard normal curve. The red dashed line represents a very small sample size, specifically 2 degrees of freedom. Notice why its tails are so thick at the edges? This represents a higher chance of extreme values occurring because of our limited data. The blue dotted line shows a slightly larger sample size, and it grows taller and thinner. Eventually, with a large enough sample, the t-distribution becomes completely indistinguishable from the solid black normal curve. You may have noticed we mentioned degrees of freedom when looking at the curves. Let us define what that actually means. The concept of degrees of freedom is absolutely central to using the t-distribution correctly. It refers to the number of independent pieces of information that go into calculating your estimate. In simpler terms, it is the number of values in your final calculation that are free to vary. When we calculate the sample mean from a single sample, we mathematically lock in one parameter, meaning we lose exactly one independent piece of information. This single number dictates exactly which specific t-distribution curve you must use to analyze your data accurately. Fortunately, calculating this crucial parameter for a single sample is incredibly straightforward. This simple formula is used to calculate the degrees of freedom for a single sample. The symbol K represents the degrees of freedom we are trying to find. The symbol N represents the total number of observations or data points in our sample. We subtract exactly 1 because, as we just discussed, calculating the sample mean consumes one independent piece of information from our dataset. If your sample size n increases, your degrees of freedom k also increases, which physically narrows the resulting t-distribution curve, bringing it closer to a standard normal shape. Let us apply this simple formula to a real-world medical scenario. Imagine you are conducting a medical trial with 15 patients to test a new blood pressure drug. You need to find the degrees of freedom for your t-distribution to understand which specific curve to use for your analysis. Finding this number is the crucial first step before you can look up any critical values. We take our specific sample size, 15, and plug it directly into the equation. By subtracting 1 from 15, we arrive at a final value of 14. This means our experiment has exactly 14 degrees of freedom. Because 14 is a moderately sized number, our specific curve will look fairly close to a standard normal bell curve, but with slightly thicker tails. Now that we know how to calculate both the statistic and its degrees of freedom, we must recognize why this matters so much. Fisher's t-distribution is the absolute backbone of modern statistical inference for small samples. Without it, any experiment with limited data, like early-stage clinical trials or destructive testing in manufacturing, would yield wildly inaccurate conclusions. If we mistakenly use the standard normal distribution for a tiny sample, we would drastically underestimate the margin of error, potentially approving unsafe drugs or faulty machine parts. The t distribution forces us to be mathematically honest about the uncertainty that comes from knowing very little. It is the exact reason why scientific studies can still draw valid, cautious conclusions today. We have covered a lot of ground today, so let us review the most important takeaways. First, the t distribution is a wider, flatter version of the normal bell curve, designed specifically for small sample sizes where the true population spread is unknown. Second, by using the sample standard deviation and adjusting for degrees of freedom, it provides a safe, cautious way to test claims and build confidence intervals. Finally, remember that as your sample size grows, the extra uncertainty vanishes and the t distribution perfectly morphs into the standard normal curve. You now have a solid understanding of Fisher's t distribution and are ready to apply it to real statistical problems.